Have you ever looked at a Nobel Prize winner and thought, wow, that must have been just a perfectly clear, straight line to discovery?
Mhm.
We often picture these, brilliant minds having that single aha
Oh, yeah,
moment.
it's a neat story.
Exactly. But what if the real story is, well, often far messier, full of human quirks, overlooked work, surprising twists?
That's exactly it.
Today we're taking a deep dive into particle physics, and our guide is H. David Politzer's Nobel lecture. It's called The Dilemma of Attribution.
A very fitting title.
It really promises to show us the human, sometimes kind of chaotic story behind that shiny Nobel medal.
And that's the core paradox Politzer gets at. I mean, Nobel Prizes are fantastic symbols, right? They highlight major advances. They definitely spark public interest.
Absolutely.
But he argues they often present this useful fiction of linear progress, the reality.
Right.
Much more complicated, lots of different approaches, dead ends, even, people discovering the same thing independently.
Okay, so our mission today is really to unpack that complexity, looking at how scientific discovery and, importantly, attribution actually works, using some, frankly, fascinating examples from particle physics.
It's a great lens to use.
Should be quite a ride into how science really happens. So Pulitzer kicks off his lecture with this really affectionate term for the scientific community, Fratelli Fisici.
A brotherhood of physicists.
Yeah, the Brotherhood of Physicists. He talks about this global connection, this sort of mutual support. He even mentions arriving at a train station, pretty much anywhere, and being greeted like an old friend by a total stranger.
Just because they're both physicists.
Exactly. That shared passion, it really sets the scene for the kind of community he's talking about.
It's a lovely image. And it leads right into his dilemma of attribution. Because, simply asking who did it, or even defining what it is, well, it gets tricky.
How so?
Well, like he points out, genuinely independent discovery, it happens a lot, actually. And then you have the way history gets written for, say, textbooks. It often simplifies things, smooths out the bumps, just to get students up to speed quickly.
Which makes sense for teaching, I guess.
Sure, it's useful, but it can hide the messier truth of how ideas actually develop and gain acceptance.
That really resonates. Which brings us nicely to the early days of Yang-Mills theories. Now, these are fundamental, right, describing particle interactions invented way back in 1954.
A long time ago in physics terms.
But here's the thing. They were apparently ignored or just deeply misunderstood for years, even by guys like Feynman, Glashow, Salam, Weinberg, future Nobel laureates. Politzer says they found discussing them kind of embarrassing. What was going on there?
It's pretty striking, isn't it? It shows how tough it can be to wrap your head around something genuinely new. The math, the concepts behind Yang-Mills, they were just different, unfamiliar.
So they just languished.
Pretty much. Until 1971. That's when Tini Veltman and his student Gerard Hooft finally cracked the case. They provided the theoretical proof that made Yang-Mills theories workable, calculable.
Okay, so Hooft's paper was the breakthrough.
Yes, but here's another layer of complexity Politzer points out. Most physicists didn't actually understand Hooft's paper directly. It was dense, difficult stuff.
So how did the ideas spread?
They learned it mostly through Ben Lee. He became this crucial synthesizer. He pulled together his own insights, some Russian work by Fediev and Popov that hadn't gotten much notice.
Right.
And crucially, the reassurance from Hooft's paper that a solution was actually possible. Just knowing it could be done changed everything. It gave people the confidence to dive in.
That's fascinating. Just knowing it's solvable makes people try harder. It reminds me of that other incredible story Politzer tells about the Reinberg-Salam model.
Another future Nobel Prize, right?
Exactly, for unifying electromagnetic and weak forces. Yet Weinberg's key 1967 paper, apparently nobody really cited it for years. Sidney Coleman even did a citation search for Science magazine in '79.
Yeah, I remember that.
And it showed interest only really exploded after Ulf Hooft's Yang-Mills work in '71.
It's true. The groundwork was laid, but the community wasn't quite ready for it, or didn't see the connection yet.
And get this, Shelley Glashow, who shared that Nobel with Weinberg and Salam, Politzer notes he never even mentioned the model or his own contributions to it in his weak interactions course back in 1970.
That's amazing. It really shows you how nonlinear this stuff is. A major idea can just sit there waiting for the right context or maybe another piece of the puzzle before it really clicks for everyone.
It's not just about being right. It's about timing and, well, the community catching up.
Precisely. And the renormalization group is another classic example of this tangled attribution web.
Okay, what's that about?
It's a theoretical tool. Super important in physics for understanding how things behave at different scales. Think tiny particles versus big structures.
Got it.
But its development, really messy. It was invented independently by Stuckelberg and Peterman in '54, then later, again independently, by Murray Gell-Mann and Francis Lowe.
Wow. Multiple independent discoveries again.
And that's not all. You had important contributions from Kurt Szymanczyk, Kurt Cowan, Wagner and Houghton, Leo Kadanoff. Lots of people built the foundations.
But the Nobel went too.
Ken Wilson, solo, in 1982.
Yeah.
Now, Wilson's understanding and the physical predictions he made were incredibly deep, definitely Nobel-worthy, no question. But awarding it to him alone kind of obscured that whole rich collaborative history that led up to his work. It's another facet of that dilemma.
It really makes you think about how we assign credit. So with all this context, how did Politzer himself fit into this? Let's get to his personal story.
Right, his own Nobel-winning work.
He talks about asking his teacher, the famous Sidney Pullman, this innocent but inordinately profound question. Just what happens if there are no scalar fields?
A simple question, but with huge implications, it turned out.
Exactly. And that question led him, surprisingly, to start working on the Yang-Mills beta function, which apparently his friend Eric Weinberg had originally planned to do for his thesis.
Yeah, a bit awkward perhaps, but that's how research goes sometimes. And this is where we get to the famous minus sign.
Yes, the minus sign. Tell us about that.
Well, Politzer describes himself as mildly dyslexic. So he says he had to do this calculation meticulously, from absolute scratch, really paying attention to every detail, especially the signs and conventions.
Okay, careful work.
And he found a negative sign for this beta function. Now, here's the drama. David Gross and his student, Frank Wilczek at Princeton, were doing the same calculation.
And they found
a positive sign. So you have this disagreement. And Coleman, Politzer's advisor, initially seemed to lean towards Gross and Wilczek. I mean, it's 2 against 1, right?
That must have been stressful for Politzer, the student.
Absolutely.
Yeah.
Adding to the intrigue, Politzer mentions this folklore that Kent Hooft had actually announced a negative sign earlier at a conference in Marseille.
Really? So why didn't anyone notice that?
Good question. Part of it might be that most physicists were focused on weak interactions then, not the strong force where this beta function was most relevant.
Okay.
But Politzer also offers this amazing description of Kurt Szymanczyk's talks. Apparently, Szymanczyk, who might have relayed 8-Hooft's result, had this, let's say, challenging presentation style.
Oh, how so?
Handwritten slides for the overhead projector, like 25-plus lines of dense, maybe hard-to-read German handwriting and equations on each one.
Wow.
And then if you wanted to refer back to an equation, you just slap a second slide right on top of the first one, but offset by half a line.
You're kidding. That sounds impossible to follow.
Exactly. So you can imagine maybe 8-Hooft's result mentioned in passing during a talk like that. Well, it might easily have gotten lost. It really highlights how communication, even just presentation style, can impact science.
No kidding. Presentation matters. So the minus sign was out there, maybe, but unconfirmed and unnoticed.
Pretty much. Until Politzer and Gross and Wilczek did their calculations. Now, when Ken Wilson heard about their results, the disagreement initially, then the convergence on a negative sign, he instantly knew who to call.
Oh.
Turns out, several other groups around the world had technically already done the calculation. Not because they were focused on the beta function itself, but en passant, as Politzer puts it.
Meaning?
Like, as a side calculation, a small part of bigger computations they were doing on radiative corrections, probably related to weak interactions. They hadn't realized the significance of that specific minus sign.
So they had it in their notebooks somewhere.
Exactly. Wilson called them up, they checked their notes, and boom, they could quickly confirm. Politzer's minus sign was correct.
Yeah.
Gross and Wilczek soon found their error too, confirming the result.
So this minus sign, why was it the crucial piece?
Because it signifies something called asymptotic freedom. It's a very counterintuitive property for a force.
Yeah.
It means the strong nuclear force, the one holding quarks together inside protons and neutrons, actually gets weaker when quarks get very close together.
Weaker when closer. That seems backwards.
It does. Usually forces get stronger when things get closer. But this weakening at short distances was exactly what was needed to make sense of certain high-energy experiments. And it meant the force gets stronger as quarks try to separate, which explains why we never see isolated quarks. They're confined.
Okay, so that minus sign, representing asymptotic freedom, basically proved that a specific type of theory, non-abelian color SU3 gauge theory, was the right description for the strong force.
Precisely. And that complex name is what we now usually just call quantum chromodynamics, or QCD. It became the theory of strong interactions.
And who were the first to really grasp its importance?
Steve Weinberg saw it immediately. And Murray Gell-Mann, too, who actually had already invented the theory with Harold Fritsch and even called it QCD. They just hadn't been able to prove it was the correct theory until asymptotic freedom came along.
So instant acceptance then. Everyone just said, aha, QCD it is.
Not quite so smooth. There were some initial experimental results that seemed to contradict QCD. Things like the electron-positron cross-section and what happens when protons collide at high energies.
Oh. So there was still skepticism.
Definitely.
Right.
Dick Feynman, for example, was famously skeptical at first. It took him a couple years, working closely with Rick Field to carefully reanalyze the experimental data before he became convinced that QCD actually did fit the facts.
Even Feynman needed convincing. That says something.
It does. It shows how rigorous the process is. And this leads to another great anecdote, the charmonium story.
Right, you mentioned Ken Wilson being cryptic in Aspen in 1974.
Exactly. He made these comments, it's charm and it's not short distance. Very mysterious.
Sounds like something out of a spy novel.
Kind of. Politzer and Tom Applequist decided to figure out what Wilson meant. And by the end of that summer, working out the consequences, they saw how QCD could explain some puzzling experimental results, specifically related to this idea of a new type of quark, the charm quark.
And meanwhile, the experimentalists.
Ironically, Politzer mentions Burt Richter, the leader at the SLAC accelerator, was actually touring the country saying he discovered the electron was a tiny hadron, completely missing what his own experiment was about to reveal.
Wow. Okay, so what happened next experimentally?
Things exploded in November 1974. Two huge announcements, almost simultaneously. At SLAC, Burt Richter's group announced a new particle they called psi.
Okay.
And at Brookhaven, Sam Ting's group announced a particle they called J.
Two different names?
Yep. Turns out it was the exact same particle, a bound state of a charm quark and its antiquark, precisely the kind of thing Politzer and Applequist had been working on. Ting called his the J particle. Richter called his the psi. We now call it the JPIs.
So Politzer and Applequist had the theory ready.
They did. They rushed to get their paper explaining it into Physical Review Letters, the top journal. But it got rejected initially.
Rejected? Why?
The senior editor, Cy Pasternak, objected to a word they used, harmonium. He thought it was frivolous terminology and against journal policy.
Charmonium. That sounds like a perfectly descriptive name now.
It does. It was coined by their friend Alvaro de Ruggiero and perfectly captured the idea like positronium, but for charm quarks. Anyway, Shelley Glashow had to step in and broker a compromise just to get the word allowed in the text of the paper.
What a bizarre hurdle. Did the delay matter?
It did. It meant their paper, which had the correct theoretical explanation, came out alongside several others, instead of right after the discovery was announced. A real shame.
But their explanation was key.
Absolutely. Understanding charmonium, this JP-type particle, using QCD, convinced most of the remaining skeptics. It cemented QCD's place. And Richter and Ting got the Nobel Prize very quickly for discovering the particle.
And Politzer actually apologized publicly to Applequist later for that delay.
Yes, in his Nobel lecture. He felt bad about it, highlighting the, human and sometimes frustrating side of scientific publishing.
It's not just about the science, is it?
Yeah.
Bureaucracy, personalities.
Never just the science. And there were other conceptual battles, too, like getting people, especially older physicists like Gell-Mann and Weinberg, to accept that quarks could have mass, even though they're never seen alone.
Why was that hard?
Because the theory of confinement was still developing. And then you had more independent discoveries about heavy quarks, like crucial work by Nathan Isger and Mark Wise on new symmetries. It was a busy, complex time.
But by the mid-70s, the dust was settling.
Yeah, by then, QCD was pretty much established.
Yeah.
And that completed what we now, almost boringly, call the standard model of particle physics.
The theory of almost everything except gravity, basically.
Right. It describes all the known fundamental particles and forces we experience directly at particle scales. A monumental achievement.
Okay, so standard model complete. End of story for theoretical physics. Apparently someone thought so.
Ah, you're thinking of Stephen Hawking.
Exactly. Late 70s, he gives his inaugural lecture as Lucasian professor at Cambridge Newton's old chair.
A very prestigious position.
And the title of his talk is The End in Sight for Theoretical Physics. And his answer was?
Basically, yes. He thought they were getting close to a final theory.
What?
Well, fast forward a few decades, and astronomical observations have completely turned things on their heads.
How soon?
Remember Isaac Newton, the second Lucasian professor? His big thing was that the heavens and the earth are made of the same stuff and follow the same laws.
Right, universal laws.
For centuries, that seemed true. But now,
Mhm.
it looks like maybe both those ideas are profoundly wrong, at least on the largest scales.
What do you mean?
We now believe most of the matter in the universe isn't the normal stuff that makes up stars and us. It's invisible dark matter. We don't know what it is, but it's not standard model particles.
Okay, so the stuff is different. What about the laws?
And the dominant force driving the universe's expansion on large scales seems to be this mysterious dark energy. It's not gravity as we know it. It's not any of the standard model forces. It's accelerating the expansion.
So most of the universe is made of stuff we don't understand, governed by forces we don't understand.
Pretty much sums it up. So much for the end being in sight.
Which brings us to a really tough problem Politzer touches on. Actually doing the experiments needed to probe beyond the standard model.
The cost problem, yeah.
He mentions $10 billion for the last big U.S. accelerator project that got canceled.
Yeah.
And to get to the energies needed for, say, string theory or grand unification, the numbers become astronomical, like $10 to the power of $22.
Which is, yeah, basically impossible. More money than exists.
It's a huge barrier, this financial wall, something, as Politzer says, few people like to discuss.
It's the elephant in the room for fundamental physics. How do we make progress experimentally when the next steps are potentially unaffordable?
And this loops back perfectly to Politzer's main point, doesn't it?
It really does.
Yeah.
He gives credit to the Nobel Foundation for its care and wisdom, but he insists that the reality of how science moves forward is just often very complicated.
The messy human story again.
Exactly. And he stresses how important it is for the public and for scientists to understand not just the scientific ideas, but the process, how they really developed, relying on these personal accounts, the near misses, the lucky breaks, the arguments, all of it.
So reflecting on this deep dive into Politzer's lecture, it's really peeled back the curtain on the human side of science. It's not this clean, logical march we sometimes imagine. It's chaotic, collaborative, sometimes frustratingly slow, sometimes surprisingly fast.
Absolutely. It highlights that fundamental tension, doesn't it? Between the simplified story we often tell the story of prizes and heroes and the much richer, messier, more collaborative reality of how discoveries actually happen, how ideas gain traction, how credit gets assigned, rightly or wrongly sometimes.
Which leaves us with a pretty big question, especially thinking about those costs and complexities we just discussed. Given how hard and expensive fundamental physics research is becoming, from figuring out who discovered what, to just affording the next experiment, what kinds of new approaches, maybe different structures entirely, might science need to keep making those truly groundbreaking leaps in the future?
That's the multi-billion, maybe trillion-dollar question, isn't it?
Definitely something to think about.